Hey, good morning or good afternoon, wherever you are. Welcome to today's deep dive maintainer track for SPIRE. My name is Andrew Harding, and I work at Hewlett Packard Enterprise, and I'm a full-time maintainer of SPIRE. In this session, we're going to explore a few ways to deploy SPIRE and build a reliable identity plane for your infrastructure. Before we get into it, I want to first apologize in advance for any mistakes or problems due to the pre-recorded nature of this presentation. Presenting in this way is new to many of us, so I appreciate your patience and leniency. Okay, so if you're attending this session, you should probably be at least superficially familiar with SPiffy and SPIRE. If that isn't the case, you may want to look up some introductory videos from earlier KubeCon events to get yourself familiarized. You can also, of course, go to the spiffy.io website to learn more. So if you're attending KubeCon, you're probably a bit like me and you have an interest in technology that facilitates deploying software at scale and provides highly available infrastructure. Today, we're going to discuss strategies for deploying SPIRE to meet that kind of a need, and we're going to discuss and focus on two main aspects. The first is load distribution. Specifically, how can we deploy SPIRE in order to distribute load related to workload registration and identity management? And as we scale up the number of workloads that SPIRE is servicing, how do we ensure that SPIRE and the issuance of service identity doesn't itself become a bottleneck as we scale out your application? The second aspect we'll be focusing on is fault mitigation and isolation. As much as we hope for perfect infrastructure, the reality of the situation is that hard drives fail, networks break, data centers catch fire, power's lost, developers write bad code, bad configuration gets deployed, etc. So how can we deploy our SPIRE infrastructure to minimize the impact of these events so that they are more of an inconvenience than a catastrophe? So before we talk SPIRE large scale, let's take a step back and do a quick recap of the essence of what SPIRE provides at the most granular scale and what it is exactly that we want to ensure reliability of as our SPIRE deployment grows. SPIRE is a reference implementation of the SPiffy specification. Fundamentally, what this means is that SPIRE, particularly the SPIRE agent, provides the SPiffy workload API. Now, workloads leverage the workload API to obtain a couple of different things. The first is a SPiffy verifiable identity document, or SVID for short. An SVID is a document with which workloads prove their identity. The SVID contains a SPiffy ID, which represents the identity of the workload. SVIDs are authenticated using authorities from the trust domain from which it was issued. This brings us to the second thing workloads retrieve over the workload API, which is the SPiffy Bundle. Again, this bundle contains X509 and Jot authorities that are used to verify SVIDs. One important aspect of the workload API is that as these SVIDs or the SPiffy Bundle are rotated or updated, those updates are streamed back to the workload over the workload API, giving the workload an up-to-date view of its identity and the material it needs to authenticate other identities. The ultimate goal of building out robust, highly available SPIRE deployments is to ensure that this relationship between workloads and the workload API can be maintained, that workloads are always in a position to reach out to the workload API to obtain SVIDs and bundle content. So let's begin with the most basic SPIRE deployment. The first thing we define in our SPIRE deployment is the trust domain. The trust domain is a logical construct that represents a security boundary within our organization. You could define a trust domain for each business unit, for example, or maybe around different classes of software within a business unit. The key takeaway here is that the identities issued to workloads within a trust domain are all issued by the same set of authorities and can be verified using the SPiffy bundle of the trust domain. Also, there's no requirement on how many trust domains you maintain within your organization. It's all dependent on what your needs are around security boundaries and isolation. Now, within that trust domain, we have a machine, virtual or otherwise, which is hosting some workloads. And our workloads are, of course, SPiffy-enabled workloads that leverage the SPiffy Workload API hosted by the SPIRE agent, through which they obtain their service identity and bundle information. Now, SPIRE agent does not mint Svids itself, but rather relies on a SPIRE server within the trust domain. SPIRE servers have a few responsibilities, but the primary of which is to act as the certificate authorities and Jot issuers of the trust domain. They maintain and rotate key pairs for signing X509 and Jot Svids. SPIRE agents query the servers about workloads they are responsible for, and they also issue signing requests to SPIRE server to obtain identity, or Svids, on behalf of those workloads. Now there is one more actor we need to consider in our basic deployment, and that is the database. In the fulfillment of its duties, the SPIRE server has various persistent storage needs. Let's step aside for a moment and discuss the database layer in more detail. The database layer is a critical component in a SPIRE deployment. It acts as the unified persistent storage layer for all of the SPIRE servers within that deployment. For the purpose of today's discussion, let's focus on just a few things stored by the database. The first is the SPiffy Bundle. Like we discussed earlier, the SPiffy Bundle contains the public key material for the X509 and Jot authorities that workloads use to authenticate Svids. Second are registrations. These registrations form the policy in the trust domain about what workloads exist and how to identify them and where they are authorized to run. The synchronization of these first two things, the SPiffy Bundle and the registrations, along with the signing requests for Svids that agents do, constitute the majority of the traffic and communication efforts that take place between the SPIRE server and agent. The third thing that the database stores is agent authorization information, or in other words, the authorization policy for authenticated agents. This information plays an important part in ensuring that incoming agent requests are being issued by valid agents. It's important to note that this database layer is what links up SPIRE servers within a SPIRE deployment. SPIRE servers attached to the same database have a shared view of all of the above information. Alright, so now that we've discussed the database layer, let's return to our basic deployment. We've got a SPIRE agent servicing workloads with Svids and bundle information, which that agent obtained through coordination with a SPIRE server backed by a database that holds bundle and registration information. And with that, we've got a complete SPIRE deployment. But, this deployment is nowhere close to robust. So we're going to look at a few ways to scale this up. But first, let's go over some failure scenarios. For example, what happens when the SPIRE server can no longer talk to the database? Without access to the database, there's not much that can happen within your deployment. New workloads cannot be registered. New agents cannot attest and join the trust domain. And like we mentioned before, the database contains authorization policy for agent Svids. Without access to that policy, the server cannot authenticate requests from existing agents and will deny access. This means agents cannot mint Svids for workloads or maintain up-to-date bundle and registration information. Critically, it also prevents Svids from renewing their own Svid. It prevents agents from renewing their own Svid, which means that eventually the agent may effectively lose its membership in the trust domain. And we'll talk about that more a little bit later. A failure event of this magnitude would need to be addressed very quickly. In order to decrease the chance of this failure event happening and to provide a quick failover path when it does, we want to add some redundancy in our database layer. There are a variety of options here with various trade-offs in reliability, cost, and performance. For example, we could set up and manage our own database cluster with read-only replicas and a quick strategy for promotion to master in the case of failover. We could also leverage a managed database solution like Amazon RDS or Cloud SQL or any of the other solutions offered by the various cloud providers. In any case, with redundancy or robust failover strategy in place, we've reduced the chances of a problem in our database layer and given us a path to quickly repair an outage. Next, let's discuss what happens when there's a loss of communication with the SPIRE server. Now, in this failure scenario, the outlook is still pretty bad. In fact, from an agent perspective, this scenario more or less mimics that of a loss of availability in the database. No new workload SVIDs, no updates for bundle or registration information, no agent SVID rotation. Depending on the nature of the failure, say a network failure in between agents and servers, we may still have other actors in the system that are able to talk to the SPIRE server and perform registration or other administrative maintenance. But from the agent's perspective, which is the most critical actor according to our workloads, the agent is just out of luck. Like the previous failure scenario, the deployment is in an unhealthy state that should be addressed quickly. Even so, what can we do to decrease the chances of downed or otherwise unavailable SPIRE servers from impacting our SPIRE infrastructure? The natural solution here is to scale out the number of SPIRE servers, so that if one server goes down, agents have another place to go. Operating multiple servers at scale like this isn't without its own challenges. For example, when you go to roll out new software configuration, you want to adopt a rolling deployment strategy so that a problem with the updates does not take out all of your servers at once, and you can roll back failed servers in the case there is a problem. There's a lot of collective operations knowledge out there around this sort of thing, so we won't go into that in more detail. However, despite our best attempts at shoring up the server or the database layer, no infrastructure is perfect, and there will be outages due to unforeseen circumstances. Luckily, there is a saving grace, and this is a critical mitigation for all of these failure modes, and that is where the SPIRE agent comes in. If we dig into the agent internals, we see that the agents do not mint workload SVIDs on demand. Instead, they actively maintain an SVID cache. The agent fetches and maintains fresh SVIDs for all workloads it is authorized for, independent of whether or not that workload has attempted to contact the agent through the workload API. This cache becomes an important property for surviving infrastructure outages by buying time for operators to repair the infrastructure without causing loss of valid service identity for workloads. Each SVID minted by SPIRE has a time to live, or TTL. Under healthy conditions, an agent does not let an SVID drop below half of its TTL. Agents actively check all of the SVIDs they have cached and quickly rotate them when they cross the half TTL threshold. This means that, in the face of an infrastructure outage, operators have a buffer of up to half of the smallest SVID TTL to repair the outage to the infrastructure before the SVID will expire. The TTL is a powerful knob for operators to configure. The trade-off on TTLs is between security and reliability. The smaller the TTL, the faster a compromised SVID expires. This reduces the time an attacker has to abuse the SVID for impersonation. However, the higher the TTL, the more time operators have to address infrastructure outages. Now, the SPIRE agent has two kinds of SVIDs cached. The one we've primarily focused on so far are the workload SVIDs. These are the ones that are served to workloads over the workload API, and they are primarily a concern of the data plane. When a workload SVID expires or is otherwise unavailable, this leads to workload level failures, which are the ones that are most apparent to our customers, unfortunately. The second is the agent's own SVID. This SVID is given to the agent when it enters the trust domain via node attestation. It is maintained and rotated by the agent. The agent SVID is used to authenticate requests to SPIRE servers and represents the agent's membership in the trust domain. If the agent SVID is allowed to expire, the agent will no longer be able to authenticate with SPIRE servers in the trust domain, effectively losing its membership. This means that the agent will have to rejoin the trust domain through attestation. However, re-attestation can be burdensome for most attestation methods, so allowing an SVID to lapse is not ideal. Generally speaking, TTLs for both workload SVIDs and agent SVIDs are configured to some low number of days or hours. The TTLs of these two SVIDs can be controlled independently. This gives operators flexibility with the security reliability trade-off. For example, if the workload SVID lapses, but the agent SVID does not, after the outage is repaired, the agent will be able to quickly recover since its membership in the trust domain has not been lost. For this reason, it isn't uncommon for agent SVIDs to be given a higher TTL than a workload SVID, especially if the control plane segregation makes it more unlikely that an agent SVID is compromised than a workload SVID sitting in the data plane. The takeaway here is that operators are given a choice. So to quickly summarize, database and SPIRE server reliability is critical to maintain a healthy SPIRE infrastructure. Redundancy and quick failover will go very far to provide reliability in these layers. The agent cache is the first line of defense to mitigate infrastructure outage. This is because the cache allows SPIRE to continue in its fundamental mission to provide SVIDs and bundles over the workload API while the infrastructure is being repaired. And last, TTLs are a powerful knob to adjust between the trade-off of security and reliability. Keeping the TTLs as small as possible, but no smaller, is important to survive infrastructure outage while reducing the window of impact for compromised SVIDs. So now that we know a little about failure modes and mitigations, let's go back to our simple deployment and talk scale for a while. In our simple deployment, we had a single agent servicing a handful of workloads. Of course, that isn't going to be enough. Our business is, of course, thriving and load against our workloads is climbing. In order to meet customer demand, we need to scale up the number of workloads. As the number of workloads and accompanying agents grow, the load on that lonely little SPIRE server is going to go up and up. And of course, if that SPIRE server falls over, agents are suddenly unable to obtain or rotate workload SVIDs. To increase the reliability of our system and to scale out demand, let's add a few servers to our deployment. Of course, as we mentioned earlier, SPIRE servers in a highly available deployment will share a database. Sufficient to say that a single database instance will not provide the reliability we need, so we'll need to provide some redundancy here as well. All right, now we are cooking. We've got some redundancy in our SPIRE server and database layers. This will help us prevent and mitigate those failure modes we discussed, as well as distribute load. But now we've got another problem. Our trust domain is all within a single data center or zone. Let's take a look how we can scale out across multiple data centers or zones. So on the left here, you can see Zone A has a bunch of workloads running, serviced by agents that are distributing their load across several SPIRE servers. Of course, this is all well and good, unless a whole zone has an outage. So let's go ahead and deploy SPIRE to a few more zones. And just a reminder, we're still talking about several SPIRE deployments belonging to a single trust domain. Like we mentioned previously, SVIDs within a single trust domain are minted by the same set of authorities. This means that each of these zones must have a shared view of the SPiffy bundle for the trust domain so that workloads minted in one zone can authenticate and be authenticated by workloads in other zones. Let's explore some options. When we mentioned the database layer, we talked about how every SPIRE server attached to the same database layer has a shared view, amongst other things, of bundle information. So our first option to linking the SPIRE clusters in each zone is to employ a shared database. This ensures that all zones see the same bundle. In order to understand how this works, let's go over how the SPiffy bundle is built by multiple SPIRE servers on top of a shared database. The way this works is that the SPIRE server generates the keys it uses to sign SVIDs. Concretely, SPIRE self-signs an X509 root CA for X509 SVIDs and a public-private key pair for Jot SVIDs. The X509 root CA certificate and the Jot Signing public key are appended to the SPiffy bundle stored in the database. This process is repeated for each SPIRE server every time it rotates the X509 CA or Jot Signing Key. A new key pair is generated and the newly self-signed CA certificate or public key for that key pair is appended to the SPiffy bundle. Whenever a SPIRE server is queried for the bundle of the trust domain, it returns the appended to bundle from the database, which, to reiterate, contains the CA certificates and public keys for each SPIRE server that shares that database. Going back to our multi-zone deployment, each SPIRE server from each zone will be appending to the SPiffy bundle stored in that shared database. Since the SPiffy bundle contains the public key material for each SPIRE server, any workload obtaining that bundle via the workload API can authenticate the Svids signed by any SPIRE server across all zones. Let's talk about the advantages of this kind of deployment. As long as you already have a scalable, robust database layer accessible from each zone, this can be a pretty convenient option, both in terms of configuration and deployment simplicity. It has a smaller number of moving parts than the alternatives. However, there are some potential downsides to consider. First, that shared database becomes a single point of failure for all zones. Second, the database has to handle all of the queries for servers from all zones, which definitely adds up. This can make it hard to distribute load and scale the database appropriately as the number of zones or workloads in each zone grows. The next option is to leverage the Upstream Authority plugin interface on the SPIRE server. The Upstream Authority provides a common X509 authority that all SPIRE servers use to sign their CAs. Every Svid signed by these SPIRE servers therefore has a chain of trust back to the same X509 authority or authorities from the Upstream Authority plugin. As you can see in this deployment option, each zone has its own distinct database cluster. This means that each zone has its own unique view of the SPiffy bundle, registration information, etc. However, because each X509 Svid is signed by a common authority or authorities, the X509 authorities present in the bundle for each zone ends up being the same. This again enables mutual authentication between workloads across zones. Let's take a detailed look at how the bundle in each zone is built. When configured for an Upstream authority, instead of self-signing, the SPIRE server instead generates a key pair and sends off a certificate signing request or a CSR to the Upstream authority. The Upstream authority signs that CSR and produces an intermediate CA certificate. It returns that intermediate CA certificate along with a set of Upstream root authorities back to the SPIRE server. SPIRE server then appends the Upstream root authority to the bundle in the database. Since the SPIRE server CA is an intermediate authority off of that root authority, an Svid signed by that server has a valid chain of trust back to the Upstream root authority present in the bundle. The SPIRE servers in other zones likewise get an intermediate CA signed by the Upstream authority and append the Upstream authority to the bundle in their own database. As you can see, the database in each zone has an identical bundle. Furthermore, Svids signed by each zone will be signed by intermediates that chain back to the Upstream root authority in that bundle. This is how workloads attached to any of these zones can mutually authenticate. Now, what I just described only applies to the intermediate CA used to sign X509 Svids. The story is a little bit different for Jot Signing Keys. Jot Svids are signed by independent keys that aren't part of a certificate chain of trust. This means that we cannot rely on the same sort of chaining properties that we can with X509 Svids. That being said, the Upstream Authority interface does provide a mechanism for SPIRE servers to use to publish their Jot Signing Keys to each other. When a SPIRE server generates a new Jot Signing Key, it appends the public key for that Jot Signing Key to the bundle in its own database. It also sends that public key to the Upstream Authority. Other SPIRE servers are watching the Upstream Authority for new Jot Signing Keys. They receive the Jot Signing Key of the other SPIRE server, and likewise append the public key to the bundle in their own database. This process is repeated for each SPIRE server that shares the Upstream Authority. And after that's all propagated, each bundle now contains the complete set of Jot Signing Keys for SPIRE servers which share the Upstream Authority. Before we go on, I'd like to point out that this ability to publish Jot Signing Keys upstream is an optional feature of Upstream authorities and is not widely implemented. So you have to be careful about which Upstream authority you choose if Jot Svids are important to you. The advantage of using the Upstream Authority option is that beyond providing a shared view of the SPiffy bundle of the trust domain, each zone has its own database instance to handle the queries for that zone. This makes it easier to distribute load and scale out the database layer within a single zone. Another advantage when considering tying together multiple SPIRE deployments using the Upstream Authority is that interactions with the Upstream Authority are relatively infrequent. SPIRE servers only use the Upstream Authority when they rotate their X509 intermediate CA or Jot Signing Keys, which is a configurable but relatively infrequent event. SPIRE servers rotate the signing key pairs at the half TTL point, similar to the agent and its SVID rotation strategy. The TTL for the CA and Jot signing keys defaults to 24 hours, but it isn't abnormal to have a much larger lifetime, say a week or a month or more. This means that if the Upstream Authority goes down, there's quite a bit of leniency in how fast the outage needs to be addressed. The disadvantage is, of course, that it is a more complicated setup with more moving parts and more points of failure. However, if your deployment is large, this can provide better scaling properties than the shared database. SPIRE has a few built-in Upstream Authority implementations, for example, one that leverages AWS's Certificate Manager's private CA feature. But let's turn to the third option, which is a refinement of the Upstream Authority approach, where a SPIRE cluster itself is acting as the Upstream Authority for a downstream SPIRE cluster. This is something that we call nested SPIRE. The SPIRE servers in each zone have their intermediate CA signed by the SPIRE cluster acting as the Upstream Authority. Of course, this means that SVIDs signed by each zone, again, have a chain of trust through the same authority, in this case the Upstream SPIRE cluster, which fulfills the criteria that all identities in a trust domain are signed from a shared set of roots. Nested SPIRE allows you to organize your SPIRE deployments into clusters that are largely independent. If an upstream cluster goes down, the downstream clusters stay relatively operational for the reasons we mentioned when discussing the Upstream Authority. This can be a very powerful way to scale out and isolate your deployments. There is a trade-off, however. Remember that each of these clusters has its own database. The advantage, of course, there is low distribution and fault isolation. However, if you remember our earlier discussion about what the database is in charge of, you'll recall that workload registrations are stored in the database. Each cluster is in charge of its own registrations. This may complicate things somewhat, since registrars will need to be deployed per cluster, or at least be able to register things with a per cluster granularity against the database for the specific cluster the workload's going to run in. But this reliability trade-off can be well worth it. I'll mention another benefit of using SPIRE as the Upstream Authority, which is that Upstream SPIRE implements the optional publishing of the Jot Signing Keys that we mentioned earlier. So we've talked about a few options now and how we might span a SPIRE trust domain across multiple zones, either using a shared database or an Upstream Authority. However, what do we do when those options are off the table? At this point, it may make sense to break our deployment into more than one trust domain. And how do we enable authentication between workloads in two distinct trust domains? Well, the answer here is SPiffy Federation. Federation is the process by which a trust domain gains the ability to authenticate workloads from another trust domain. It is a one-way relationship, meaning that to enable mutual authentication, each trust domain needs to federate with each other. The act of federation involves obtaining and disseminating the SPiffy bundle of a foreign trust domain to the workloads in your own trust domain. SPiffy defines an interoperable mechanism by which a trust domain can obtain the bundle of a foreign trust domain. This mechanism is the SPiffy Bundle endpoint, which is an HTTPS endpoint that serves the SPiffy bundle of the foreign trust domain. The endpoint is authenticated, and at this time we define two authentication mechanisms. The first is via Web PKI or via SPiffy authentication. As the foreign trust domain rotates its authorities, this bundle endpoint can be pulled with some frequency to maintain an up-to-date view of the foreign trust domain bundle. SPIRE distributes the foreign trust domain bundle to workloads over the Workload API, enabling workloads to authenticate SVIDs from the foreign trust domain. So our distinct trust domains can establish a federation relationship and retrieve each other's bundles and mutually authenticate. It's also worth mentioning that this deployment strategy is one way that people deploy SPIRE across cloud and on-premise data centers. Well, that's it for today. That's what I have for you. To summarize, today we've explored deployments from the very simple to multi-zone to nested hierarchies and onto federated trust domains. We've talked a little bit about failure modes and the various layers that require redundancy in order to achieve a highly available deployment that can scale. And we've also dug into the details of how bundles are built across databases or shared databases. And we've touched on the mechanisms around SPiffy Federation and the ability for two trust domains to federate with each other. So thank you for hanging in there. That was definitely a lot to go over. If you have questions, feel free to reach out on the session chat. We'll be happy to address them. You can also visit us at the SPiffy Slack, and we've got a friendly community there to help you get going with SPiffy and SPIRE. You can also hit up the GitHub pages for SPiffy and SPIRE or the spiffy.io website for more information. Thank you very much.